Acids, bases and salts. Acids. Acids are the chemical compounds that are sour in taste. Acids turn blue litmus paper to red. That means when we dip a blue litmus paper in acid, it turns red. Acids are corrosive to metals. That means acids, they cause damage to the metals. Let us see some examples of acids in our day-to-day life. Curd. Curd contains lactic acid. This lactic acid is produced in the curd by the fermentation of lactose by bacteria. Curd contains a sugar called as lactose. This lactose is converted to lactic acid by bacteria. Lemon and other citrus fruits. They contain citric acid. These citric acids give them the tangy, sour flavor to the lemons and citrus fruits. Vinegar. Vinegar contains acetic acid. Vinegar is used in cooking, cleaning and food preservation. Next, tomatoes. Tomatoes contain citric acid and malic acid. So these acids give the sour taste to tomatoes. Carbonated drinks. Carbonated drinks contain carbonic acid and phosphoric acid. So these acids give the carbonated drinks a sour, sharp taste. Apple. Apple contains malic acid. It gives the tartness or sour taste or bittery sour taste to the apple. Grapes. Grapes contain tartaric acid, which gives them their sour taste. Stomach acid. Stomach acid contains hydrochloric acid. This acid helps in the process of digestion. It is important for the activation of protein digesting enzyme, that is pepsin. So the stomach acid helps in the breakdown of food. So these are the common acids generally we see in our day-to-day life. Next, bases. Bases are bitter in taste. Bases turn the red litmus paper to blue. So if red litmus paper is dipped in bases, it turns to blue. They are soapy or slippery to touch. Let us see some examples of bases in our day-to-day life. Detergents. Detergents contain sodium hydroxide or other alkaline substances to break down the grease and oils. Toothpaste. Toothpaste contains sodium bicarbonate, that is baking soda. It neutralizes acids in the mouth and helps clean teeth. The purpose of toothpaste is to neutralize the acids created by bacteria in our mouth. Hair dyes. Most of the hair dyes contain ammonium hydroxide. So this ammonium hydroxide, it opens up the hair shaft and it helps in the better coloring of the hair. Baking powder. Baking powder contains sodium bicarbonate and is used in baking to cause dough to rise. Soap. Soap mostly made from a base such as sodium hydroxide, lye, and fats or oils. It creates a product that can emulsify grease and oils. So soap is basically made from a base, that is sodium hydroxide. Antacids. So antacids contain magnesium hydroxide or calcium carbonate. So these bases, they neutralize the stomach acid and gives relief from the heartburn and acidity. Next, bleach. Bleach mostly contains sodium hypochlorite. It is a very strong base. It is used for cleaning and disinfecting. And cleaning products. Many general cleaners, they contain the bases like ammonia to help dissolve grease and dirt. Then, how do we test the presence of acids and bases? We can test the presence of acid or base using acid-base indicators. Acid-base indicators helps us to identify which substance is acid and which substance is a base. Litmus is the most popular acid-base indicator. It is a natural acid-base indicator. It is obtained from a kind of lichens. We already learned that blue litmus paper turns to red when dipped in acid and red litmus paper turns to blue when dipped in a base. Apart from litmus, there are some other natural substances which act as indicators like red cabbage, turmeric and hibiscus and some other flowers act as indicators. These are called natural indicators. Methyl orange and phenolphthalein. These substances are also used as indicators, but they are man-made synthetic acid-base indicators. Methyl orange and phenolphthalein are synthetic acid-base indicators. When methyl orange is added to an acid, it turns to red color. That means an acid gives red color with methyl orange. If it is added to a base, its color changes to yellow. If methyl orange is added to a base, the color changes to yellow. So the other synthetic acid-base indicator, phenolphthalein. When phenolphthalein is added to an acid, there is no color change. Phenolphthalein plus acid, no color change. But phenolphthalein is added to a base, it gives pink color. Phenolphthalein plus a base, pink color. Here we have some chemical compounds. Let us test these compounds with acid-base indicators. So among these compounds, HCl, H2SO4, HNO3 and CH3COOH. These compounds, they turn the blue litmus to red. And when methyl orange added to these, they produce red color. And when phenolphthalein is added, they remain colorless. So all this indicates that these compounds are acids. The remaining compounds like sodium hydroxide, calcium hydroxide, potassium hydroxide, magnesium hydroxide and ammonium hydroxide, they turn the red litmus to blue. That means when red litmus is dipped into a base, it turns blue. And these compounds, they produce yellow color with methyl orange. And they form pink color when phenolphthalein is added to them. So all this proves that they are all bases. So far we have seen the acid-base indicators that give a color variation. Now we will see some acid-base indicators which works with smell. That is, by smelling we can identify whether the substance is acid or base. So this kind of acid-base indicators are called olfactory indicators. Examples of olfactory indicators are onion, vanilla essence and clove oil. Let us see an activity showing that how to use onions as acid-base indicators. Using onions as acid-base indicators. First, let us take a polythene cover and place some chopped onions into it. Then place a small piece of cloth in the same cover along with the onions. Now tie the cover using a thread or tape. So whatever the cloth that is kept inside this packet, it absorbs the acid from the onions. Now place this packet in the refrigerator for the whole night. On the next morning, take out the cloth from the cover. Now cut this cloth into 2 strips. Now smell both the strips. Then you will get the onion smell from both the strips. Now place the strips on a flat surface and add dilute HCl drops to strip 1 and sodium hydroxide drops to strip 2. Now rinse these 2 strips in distilled water separately. So we have to rinse them off completely. So do you know why we need to rinse them in distilled water at this step? If you know the answer, please write it in the comment section. Now once again smell the 2 strips. The strip to which HCl is added, it gives the same onion smell. But the strip to which sodium hydroxide is added do not give any onion smell. That means it lost its onion smell. Do you know why? Because the onions treated cloth strip, it becomes acidic since the vapors from the onions are acidic. So we kept the cloth in the bag along with onions. So the cloth absorbed the acidic vapors and it became acidic in nature. But when these acidic cloth strips are treated with HCl, it do not react with HCl because the cloth is having an acid and HCl is an acid. There is no reaction between them since both are acids. Whereas in the acidic cloth strip that is treated with sodium hydroxide, there is an acid-base reaction. There is a neutralization reaction between the acid-treated cloth strip and sodium hydroxide. So the cloth strip, it loses its odor. Now let us see the reaction of acids and bases with metals. First let us see the reaction between an acid and a metal. Add few zinc granules to 5 ml of dilute H2SO4. So zinc granules are metal and dilute H2SO4 is an acid. So this is a reaction between a metal and an acid. Zinc granules dilute H2SO4. They both react and forms a salt called zinc sulfate and hydrogen gas. So in this reaction they forms a salt and hydrogen gas. So acid plus metal gives rise to salt plus hydrogen gas. Now let us see the reaction between a base and a metal. Add few zinc granules to 5 ml of dilute sodium hydroxide. Zinc granules metal and dilute sodium hydroxide is a base. Now they both react and forms a salt called sodium zincate plus hydrogen gas. So here the reaction between metal and base. Base plus metal gives rise to salt plus hydrogen gas. But all metals may not react with the bases in the same way. So some metals give this output, give this salt plus hydrogen gas. But all metals do not react in the same way. All metals may not give out a salt and hydrogen gas. Now let us see the reaction of metal carbonates with acids. Take 0.5 grams of metal carbonate like sodium carbonate and add 2 ml of dilute HCl. 0.5 grams of sodium carbonate, 2 ml of dilute HCl. Now the reaction takes place and it forms a salt. What salt is formed? Sodium chloride and water and a gas. These three things are formed. Now here, whatever the gas is produced, this gas is passed through calcium hydroxide solution. When it is passed through calcium hydroxide solution, it forms a white precipitate. That is nothing but calcium carbonate. We know that when calcium hydroxide reacts with carbon dioxide, it turns into calcium carbonate. That means the gas produced in this reaction is nothing but carbon dioxide. So when a metal carbonate reacts with an acid, it forms salt plus water plus carbon dioxide. Now let us look at the reaction of metal hydrogen carbonates with acids. Let us understand this with an activity. Take 0.5 grams of metal hydrogen carbonate like sodium hydrogen carbonate and add 2 ml of dilute HCl. 0.5 grams of sodium hydrogen carbonate and 2 ml of dilute HCl. It forms a salt, that is sodium chloride, water and a gas. The gas produced in this reaction also carbon dioxide. So when a metal hydrogen carbonate reacts with an acid, it forms salt, water and carbon dioxide. So all metal carbonates and all metal hydrogen carbonates react with acids and produce salt, carbon dioxide and water. Metal carbonate or metal hydrogen carbonate plus acid gives rise to salt plus water plus carbon dioxide. Now let us see the reaction between acids and bases. Let us see an activity to understand this. Take 2 ml of dilute sodium hydroxide and add 2 drops of phenolphthalein. Since sodium hydroxide is a base, phenolphthalein turns it into pink. Now add few drops of HCl. The solution becomes acidic and the pink color disappears. Now add few drops of sodium hydroxide, the pink color reappears. So in this experiment, we have seen that by adding an acid to the base, we can reduce or completely remove the basic nature of the substance. In the same way, by adding a base to an acid, we can reduce or completely remove the acidic nature of that substance. So this type of reactions are called neutralization reactions. When a base reacts with an acid, it forms salt and water. Base plus acid gives rise to salt plus water. Now let's see the reaction of metal oxides with acids. Take a small amount of copper oxide in a beaker and add dilute HCl slowly by stirring. We have taken copper oxide in a beaker and adding dilute hydrochloric acid. Now the color of the solution slowly changes to bluish green color. The copper oxide reacts with hydrochloric acid and forms copper chloride and water. So, when a metal oxide reacts with an acid, it forms salt and water. Reaction of non-metal oxides with base. When a non-metallic oxide like carbon dioxide is passed through a base like calcium hydroxide, it forms a white precipitate called calcium carbonate. So here a non-metallic oxide, that is carbon dioxide, it is passed through a base, that is calcium hydroxide. So when they both react, they forms a salt, that is calcium carbonate. So a base plus a non-metallic oxide gives rise to salt and water. Now let us see the common things in both acids and bases. To know the common thing in both acids and bases, we need to perform an experiment. Take some dilute HCl in a beaker and fix 2 electrodes. Now connect these electrodes to 2 wires. To one of the wire, connect a bulb. Now connect the free ends of these wires to a power source and let the current flow. Now the current flows through the solution and the bulb glows. Now replace the contents in the beaker with glucose solution. Earlier we have taken HCl, so in place of that we are taking glucose. Now the bulb does not glow. Again replace the glucose with alcohol. Even with alcohol, the bulb does not glow. Now again replace this alcohol with sodium hydroxide. Now the bulb glows. In this experiment, the bulb glows with HCl and sodium hydroxide and it does not glow with glucose and alcohol. This shows that acids and bases conduct electricity. Do you know why? Acids and bases, when dissolved in water, they produce cations and anions. Cations are the positive ions and anions are the negative ions. When HCl is dissolved in water, it produces cations as H+ ions and anions as Cl- ions. Anyway, the hydrogen ions cannot exist alone, so they exist in the form of hydronium ions. In the same way, if we dissolve sodium hydroxide in water, it also forms cations and anions. Sodium hydroxide forms Na positive cations and OH- anions. So this is the common thing in both acids and bases. That is, they both dissolve in water and form anions and cations and they conduct electricity. Now let us see dilution. If we mix an acid or base with water, it results in the decrease in the concentration of ions per unit volume. This process is called dilution. Dilution is an highly exothermic reaction. We know that exothermic reaction means heat is released. So when acid or base are mixed in water, then high amount of heat is released. So we should be careful while adding acid or base to water. Always add acid to water slowly by stirring. Never add water to acid. If water is added to acids, it splashes out and causes burns due to local heating. Now let us look at the strength of acids and bases. All acids do not have the same strength. In the same way, all bases do not have the same strength. Then how do we know the strength of an acid or a base? We can know the strength of an acid or a base using pH scale. pH scale has values from 0 to 14. The substances with pH 7 are neutral. The substances with pH below 7 are acidic, and the substances which are above 7, that is from 7 to 14, are basic. The acids that are closer to 0 are strong acids, and the acids that are closer to 7 are weak acids. In the same way, the bases that are closer to 14 are strong bases, and that are closer to 7 are weaker bases. Now let's see the importance of pH in our daily life. The pH of water in water bodies is very important for aquatic life. Acid rains make the water bodies acidic, which causes a great damage to the water plants and animals. Plants need a specific pH for their healthy growth. Farmers test the pH of the soil from time to time to add the necessary chemicals which are missing in that soil to ensure proper growth of plants. Importance of pH in our body. Our stomach produces hydrochloric acid. This acid helps in the digestion of proteins. It activates an enzyme called pepsin in our stomach which digests the proteins. This acid also kills the germs that enter along with our food. If this hydrochloric acid is produced in large quantity in our stomach, then it leads to a condition called acidity. Acidity causes stomach burn. So to reduce the stomach acidity, certain antacids are used. So in making these antacids, bases like magnesium hydroxide are used. Next, our tooth enamel is made up of calcium hydroxyapatite. So this substance is dissolved by the action of acids that are produced in our mouth. But how acids are produced in our mouth? The bacteria in our mouth feeds on the sugars that we eat and produce acids. And these acids reduce the mouth pH below 5.5. So at this pH, it causes tooth decay. Certain living things use acid bases for their defense. For example, bee sting has an acid which causes pain and irritation. So to this, as a remedy, we can use a base like baking soda. So for a bee sting, we can apply some baking soda to reduce the action of that acid. In the same way, nettle leaf sting also has an acid and causes rash and pain. Its acidic effect can be neutralized by rubbing that area with a dog plant. Now let us learn about salts. What is the pH of salts? Are salts neutral, acidic or basic? Some salts are neutral, some are acidic, and some salts are basic in nature. Salts of strong acid and strong base are neutral with pH value of 7. Salts of strong acid and weak base are acidic with pH value less than 7. Salts of strong base and weak acid are basic in nature with pH value more than 7. Strong acid, strong base, they are neutral. Strong acid, weak base, acidic. Strong base, weak acid, basic. Now, let us learn about the important salt, that is sodium chloride. Since it is used in our day-to-day life, it is also called as common salt. But do you know that it is the main ingredient in preparation of many chemical compounds in industries? Sodium chloride is used to make sodium hydroxide, that is caustic soda, sodium hydrogen carbonate, that is baking soda, sodium carbonate, and calcium chloride, that is bleaching powder. First, let us see sodium hydroxide. When electricity is passed through an aqueous solution of sodium chloride, it produces 3 products. They are sodium hydroxide, chlorine gas, and hydrogen gas. This process is called chloralkali process. In this setup, chlorine gas is produced at the anode and the hydrogen gas is released at the cathode side, and the sodium hydroxide is formed at the cathode. Use of products formed in this chloralkali process. The chlorine as produced in this reaction can be used for water treatment, swimming pools, manufacture of PVC, disinfectants, chlorofluorocarbons, and pesticides. The hydrogen gas released in this reaction can be used as fuel and in making of margarine and fertilizers. Sodium hydroxide is used in degreasing metals, making soaps and detergents, making paper, and in making of artificial fibers. In all these cases, sodium hydroxide is used. Next we see baking soda, sodium hydrogen carbonate. When common salt, that is sodium chloride, is treated with water, carbon dioxide and ammonia, it gives ammonium chloride and baking soda. NaCl plus H2O plus CO2 plus NH3 gives rise to NH4Cl, that is ammonium chloride plus NaHCO3, sodium hydrogen carbonate, that is baking soda. So this baking soda is used as an cooking ingredient and it is also used as an antacid. Sometimes it is used in fire extinguishers also. So do you know why baking soda is added to food items? When baking soda added foods are cooked, the sodium hydrogen carbonate becomes sodium carbonate plus water plus carbon dioxide. So when sodium hydrogen carbonate is heated, carbon dioxide gas is produced. This carbon dioxide gas, it makes the food items spongy and fluffy. Washing soda, sodium carbonate. Recrystallization of sodium carbonate gives washing soda. Na2CO3 plus 10H2O gives rise to Na2CO3 10H2O. Let's see the uses of washing soda. It is used in glass, soap and paper industries. It is also used in manufacture of borax. This borax is used as a cleaning agent. It is more alkaline than the washing soda. Washing soda is also used as a cleaning agent. It helps in the removal of water hardness. So that is to treat the hard water, washing soda is used. Bleaching powder, CaOCl2. Calcium hydroxide is treated with the chlorine gas, which is produced during chloralkali process to prepare bleaching powder. CaOH twice plus Cl2 gives rise to CaOCl2 plus H2O. This bleaching powder is used in whitening of cloth, paper, jute and linen fibers in their manufacture. Usually, cloth, paper, jute items are manufactured from the ingredients which are not white. They have yellow or light yellow tint. But by using the bleaching, they make them appear white. Bleaching is also used in industries as oxidizing agent. It is also used as a disinfectant substance. The white powder that is sprinkled near public toilets and garbage bins is nothing but bleaching powder. Next, plaster of Paris, CaSO4 1/2H2O. Manufacture of plaster of Paris. On heating gypsum at 373 Kelvin, it loses water molecules and becomes calcium sulfate hemihydrates. It is called as plaster of Paris. CaSO4 2H2O plus heat gives rise to CaSO4 0.5H2O plus 1.5H2O. Do you know why it is called as plaster of Paris? In 18th century, extensive mining of gypsum was started in Paris for the large-scale production of plaster. Plaster is used in the process of construction. Since then, it is being called as plaster of Paris. Uses of POP. It is used by doctors as a plaster to support the broken bones. It is also used to make toys and models.